Hello and welcome to my presentation on 3D printing with steel additive manufacturing for connections and structures. As you can see in the little video that's here in the first slide, we print with steel and we can print bars like here and structures and all kinds of things, and I will present this to you within the next 25 or 30 minutes. I will start with answer to the question how to print with steel. What do we need to print with steel? Then I will go on to the automated production. How can we include this printing into steel fabrication and production? After that, I will show you some examples on what to print, what I think is reasonable to be printed. And coming from this, we have some ideas on topology optimization, which I will show to you before I close with some videos and slides on our additive manufactured bridge that was built 1.5 years ago here in Darmstadt on the premises of our university. So here you can see printing as it is done with steel. We have so wire being the printing material, and it's a gas shielded metal arc welding as it is commonly used in steel fabrication. So that's a little time-lapse video you see here, and you see we can print whatever shapes we want to be printed. So this is called wire and arc additive manufacturing, WWAM, and we can print up to 10 kilograms per hour if it goes into the right direction. If you print something horizontal, as we will see later, it will go down to maybe 1.5 or 2 kilograms per hour, but that's quite a good result. In average, if we build it upright, as you can see here, it will be up to 5 kilograms an hour, or even bigger, more. The most popular and I think well-known 3D printed structure is this bridge by MX3D, startup from the Netherlands based in Amsterdam, and their bridge was opened in July of this year. And I think that's very, very good example of what you can do with 3D printings. You can do steel in very, very free forms without any cast iron. And I think our colleagues from Amsterdam did a very good and great job with this bridge. But just to be not too modest, we printed our bridge 1.5 years earlier in fall of 2019. It's smaller, it spans only 3 meters compared to the 11 meters of the bridge in Amsterdam. But our bridge was printed on site in contradiction to the one printed in Amsterdam that was printed vertically in a large hall. Here it was printed horizontally. So that was, I think, the first bridge worldwide that was printed on site. But I will come back to this later on. Where do I see a future in steel construction and structural steel engineering? I think that's the automated production that has started already. We have 2 or 3 competitors on the European market who produce automated steel production, where they have robots doing welding and handling and the turning around of the hot rolled I-beams or welded beams. Here you can see on the left-hand side one robot holding a stiffener plate and the other one welding. That's a system that uses 2 to 3 robots. On the right-hand side, you have a system that uses 3 welding robots and 2 handling robots. And there you can see that at the end of the structure, head plate is welded by the welding robot, while on the center you can see a little bit the shining of the welding stiffener is also welded into place. So I think this automated production just calls for WWAM 3D printing, because now we can print into an I-beam whatever part is needed, head plate stiffeners and so on. So what is the advantage? If you look at the current way we are producing, we need steel plates with different thicknesses, and they must be held in stock. And these might be plates with 10 or 20 or even 50 millimeters for head plates or base plates. And maybe you need just 3 or 4 plates, but they have to be cut and drilled out of a large plate. This plate has to move into the cutting and drilling equipment, and you get some disposal, or you get some plates where just a few head plates or stiffeners have been cut out, and they need to be stored intermediately. And so you have a lot of logistics. A forklift truck or crane has to move the things back and forth. And finally, the handling robot has to measure the plates to identify them and to put them in the right position. And all this is no longer required. All we need is wire or printing material and gas, the shielding gas, to give a good quality of the final result of the printed product. And we usually use a wire with 1 millimeter diameter. It's a G3SI1, so that's a mild steel that results into S235 or S355. So it's very good normal steel, as it is used for welding in everyday steel production. I will come back to the quality of the steel, the result we get with 3D printing later on. We saw one first point when we started with that. That was rolling tolerances of the hot rolled beams. We see quite often missing parallel flanges or misangles, misalignments of the flanges, and that makes it difficult to place the stiffener into its position, as you can see here. On the right-hand side, you get a big gap. On the left-hand side, you might not get a gap at all. You might have to mill a little bit, so people in the workshop have additional work to fit the stiffener into place. And unfortunately, due to the rolling tolerances we saw in recent years, that happens quite often. This can be avoided if we use 3D printing. Here you see a stiffener on the left-hand side that was printed into a hot rolled beam, and on the right-hand side you see traditionally manufactured stiffeners. And we took the normal conventionally manufactured stiffeners and tested them, which gave ultimate load, in this case of 591 with a standard deviation of 33 kilonewtons. We did the same with the same thicknesses of the plates with wire and arc additive manufacturing. We had a little lower mean value, but that always depends on the thickness you program. Here we had a little smaller thickness of the WWAM compared to the stiffener. Interesting is small standard deviation in 3 tests. We had only a deviation of 8 kilonewtons, so much smaller than with a conventional. And if you see the ultimate load without a stiffener, it's 185 with a standard deviation of 9 kilonewtons. So the WWAM product seems to be promising. You avoid all your logistics. You don't have to keep different plate thicknesses available in stock. You just weld in place what you need. And if you go back to the slide where you see these automatic production systems, where we have systems with 3 welding robots. Not all of these 3 welding robots are needed all the time to weld some head plates or something like this. So 1 or 2 of these robots will have enough time to weld in place or print or additively manufacture a stiffener, as you see it here. So this is just a replacement. It's a replacement of a thing we have already. So that's, for me, the first step in additive manufacturing, to look at what we have done so far, how far we are currently in steel fabrication. The next step is to see what might be improved a little bit. Where can we use additive manufacturing to do something new? And here we come to the double angle connection, as you can see it here. Pin-ended connection of a beam, which uses 2 angles that are bolted to the web of the beam and to the flange of the column. Our idea here was to print a hook and a bolt, to print a hook onto the flange of the column and a bolt onto the web of the beam. And here we can obviously print much bigger bolts, so we are not restricted to the normal bolt sizes that are delivered by the bolt industry. We can produce much bigger diameter. So 1 bolt on the left and 1 on the right hand side of the web will be enough, and this hook will be printed onto the web of the column. And as you can see in this little video, we just place it on site. So even the erection is much faster, because you need nobody who will climb on a ladder or on some scaffolding or whatever to bring the bolts into place and tighten the nuts and all this. Of course, you can say, oh, well, what can you do on the opposite side? You cannot put this into place like this, because each beam has 2 sides, 1 on the left and 1 on the right hand side. And if you lower it vertically, the lower flange will be a problem. But one thing, you can cut off the flange, or there's another solution which I cannot show in this video. So I think that is possible to make easy erection with this system. To show that it's feasible, here you see a printed hook, or a double hook that is printed on the flange of a profile. And here you see a test we did on this. So you see the hook that is bolted to a load introduction, and here you see the compression, how we can put a large force in it. And this hook was designed for 70 kilonewtons. It finally failed at 100 kilonewtons. And as you see in this little video, the steel behaves very ductile. So you don't get the brittle failure that you might expect if you have a welded connection, but you saw that we have a very ductile behavior, large deformations before the weld between our 3D printed hook and the flange of the column failed. That's where you expected it, on the top side where you get tension or stress. There we had failure in this case. But what was for me very impressive was the very large ductility of this hook. And let me try to start it again, that you can see it again. Here we see it. So we get large deformations because before we have the failure of this connection. So That's, for me, the second step if you think about additive manufacturing, and if you design using the possibilities additive manufacturing gives to you. The third one is to open up our mind for totally new structures, to use the ability of 3D printing, of additive manufacturing, in optimizing the topology according to the loads and to all the other restrictions we have. And we did this with a head plate, a T-stub connection. And here, again, you see in a short video what we printed and how it works. We printed the red structure onto the flange on the top and lower side of the top flange. And afterwards, we can bolt it with normal bolts that are loaded under tension. So it's a replacement of the head plate. And in this third step, in this topology optimization, we get a totally new structure. We don't replace a stiffener by a new stiffener. And you see here in this red structure, you get little tension legs. So it's not the bended T-stub as we know it from a head plate connection, but we get more tension, less bending. And this leads to a tremendous optimization and a tremendous reduction in the material. If you look at this graph, you see on the left-hand side, if we use as much material as we use for the head plate, we get approximately 50% more ultimate load, nearly 50%. And if we reduce the mass, somewhere in the area of 35% of the original mass, we get the ultimate load that the common head plate has. So it's a large reduction in material, and that's good looking from the printing part, because as I said very early in the presentation, we print up to 10 kilograms per hour. In average, in small structures, as we see it here, we come closer to 4 or 5 kilograms per hour. So every kilogram we saves us production time. Not only material makes it faster and makes it interesting for automatic production. And here you see, with a totally new approach, with a new idea, with topology optimization, we get small printed volumes that can be very well introduced into automatic fabrication. And that's, I think, a very big step forward. And here you see the connection as it was printed, and we also tested it, but you can see some of the test results in other publications. Another point that I wanted to show to you are these clamping elements that are used to fix wind bracings around steel. And in the web, you use these cast iron plates, as you see in the center top, two elements, and in the center bottom, you see how they are put into place. So this half moon shape is welded to the flange. And then you have this special plate where you can fix a nut and a washer and introduce your wind bracing forces. You can also print this, again, topology optimized, in exactly the angle you need. And you don't need these two cast iron elements that have to be put into place. They have to be welded. And again, you save all the logistics. And you see here the final result as we printed it. These clamping elements printed them onto the web of a hot-rolled I-beam. This is also a small welding volume. Not much mass can be welded very fast. So it takes not much time in automatic production, and you can, I think, introduce that very fast with a direct flow from your design software into the production software. We also printed some larger structures here. You can see a tube 1 meter, approximately 1 meter high, 60 millimeters diameter, 3 millimeters wall thickness. In the center picture on the left-hand side, so you see a normal hot rolled tube, and on the right-hand side, you see the 3D printed tube. Here you can see the printing process again in a time-lapse movie. I think you can do this if you need some very special geometry, as I showed it in one of the first pictures. If you have not a normal round or rectangular tube, but if you want something with 6 or 7 corners and all kinds of things, then it might be interesting. But here you have quite long printing times. Even if in this way you can print up to 9 or 10 kilograms per hour, you need much time, and you just get an advantage if you print such a extraordinary geometry as the MX3D bridge that was printed in Amsterdam, or some special arch-shaped column. The ultimate load was the same, nearly the same. We expected from the additive manufacturing, with all the eigenstresses from the heat-induced eigenstresses, that the additive manufactured column might have a lower ultimate load, but it had approximately the same as a hot rolled column. So that was a very successful project, but as I said, that's only interesting for strange shapes, odd shapes that we don't get with hot rolled or cold bent products. Let me show you the result of another project with special steel nodes. We thought about fabricating special nodes for 3D structures. You see what we plan to do. In phase 1, we want 4 members to be joined in one plane, rectangular to each other, but in the next step, not rectangular, and in the third step, not continuous. So one is not straight, going straight through. Phase 2, we will have 4 members in 2 planes, and phase 4, we have 4 members in any direction. And here you can see in the little green area, there is one central node where the 4 members have to be bolted to, and on the right-hand side you see structures where we might need some nodes like here. And here we see 3 printed nodes that were printed by our research partners at the university in Ilmenau and by Gefertec, 3D printing company in Berlin, in Germany. What's interesting is, if you look at the inside of these nodes, they always have a different geometry depending on the loads. On the left-hand side, we have 4 members coming with the same moment and the same normal forces, same shear forces, so you get a very symmetric structure. In the center, on the right-hand side, you have different moments and different normal forces, different shear forces coming from the 4 members. So you can react to this by different filling inside, and in the final step, of course, 4 plates can have different angles to each other, and you make these nodes, and that makes it quite easy to bolt straight beams to them. In this project, we also did some material tests. Here you see this A-shaped test specimen, and you see how we did some coupons out of that, and we get yield strengths above the 355, which was our goal, and ultimate stress also much higher than is needed for S355. And you see we get quite some good strain results, 15 to 20%. So that 3D printed material in the direction of the printing, or orthogonal to the printing direction, we get very good results, better than we expected. Let me come to an end with a little bridge we built in Darmstadt. And so left-hand side, you see the model, and the right-hand side, you see the setup on a little creek here in Darmstadt on the campus of the university. We had a printing robot. We had a span of about 3 meters because that was the span our robot was able to cover. And it was printed from the left-hand side to the right-hand side. And here you can see a little video how our robot was printing on one side of this bridge. We changed printing from the left-hand side to the right-hand side because that gives us some time for cooling. If you print horizontally, it's very important that you have enough cooling time so that the freshly printed drop of steel will cool and not fall down and drop into the water. So we need a very special welding system. This was a CMT welding method. And if you print left-hand side to right-hand side, that takes a little longer time because the robot has to move back and forth, but that gives the other side enough time to cool down. So if we put on the next drops, they will cool down also and not drop into the water. We try to improve the cooling by sprayed water, not only compressed air. And you see that compressed air and sprayed water had no significant influence on the hardness. We have a bigger hardness of 161 to 163, and also the microstructure is very similar. So the cooling with sprayed water improved the production time, reduced it, but had no negative influence on the material characteristics. Okay, so to sum it up, I showed you what we think is wire and arc additive manufacturing, how it works, what it has for great possibilities in steel fabrication applications, automated steel fabrication, how we can integrate it, how we can replace like stiffeners, existing structures or design elements, but also how we can develop totally new ideas like this head plate structure that was found by structural optimization, topology optimization. We have some very promising first results, not only with regard to the geometry, but also to the strength and the ductility and the hardness of the material. So I think we are on a good way to open a new window for steel fabrication to give us more possibilities to make it faster and to make new geometries and give some ideas for a new development. I see two challenges coming up. One is designing these connections according to Eurocode part 1993-11 and 1.8, and to produce according to EN 1090 part 2. We are not included in these codes with additive manufacturing, and I see that as a goal that we have to develop some rules to make all that available for everyday steel design and fabrication. Okay, thank you very much. I want to close with this picture of our little bridge that was also crossed by the people who printed the bridge, but this is our iconic picture with the 3 little ducks. And thank you very much to Fronius, WDI, Messer, and Goldbeck for supporting our research. And if you want to see some more of that, you can visit us on YouTube or Instagram or wherever you are at Additive Manufacturing Technical University of Darmstadt. And thank you very much for your interest and for attending this presentation. And I hope to see some interesting questions which I hopefully can answer.